Well, good morning. I'm Craig Settle, Regional Manager of Western Canada with Excell Battery Company. Today, I'm joined by my counterpart, Bob Fay, our Regional Manager with our Houston facility, and Excell's own esteemed Director of Engineering, Mike McWillie. I want to thank you all for inviting us into your offices and, in many cases these days, homes. Connecting with you folks that put rubber to the road is one of the things that Excell holds most dear. So before we get started, I just want to affirm to you that we here at Excell are always excited to hear from you and do so greatly enjoy our many collaborations around the challenges that the everyday and not so everyday bring to your door. You're all doing the great work of creating the activity, energy, vigor of the industries that make the world go round, and we endeavor to help you keep that spark striving ever forward. So do reach out, keep connected, and whatever your demanding application, together we'll get that job done. So today we're going to discuss high temperature batteries. I will build us up from the basics and set the stage for the various technologies that exist out there. Bob Fay will go through the elements and considerations of cell construction. Mike McWillie will take us down the path of performance challenges that you as operators and designers should be aware of. Bob will go over some safety concerns and implications. And finally, we will all address the questions and answers that you have submitted during the Q&A or in the Q&A during our conversation. So do get your questions in as this conversation goes along. So many of you who are looking at these types of high temperature batteries are in that oil patch type of application. And I think we can all appreciate that in that world, we need the most energy and the highest level characteristics in these applications. The voltage, the density of energy, the temperature rating, the current capability, and just sheer ruggedness. I often say that aerospace often has a higher spec, but in the day-to-day, it's the oil patch that probably has the most demanding application in the world. So yes, what is a battery? It's 1799, and Alessandro Volta invents the Volta pile, which you can see over there. That was essentially our first electrochemical cell with plates of copper and zinc. If we cast our memories back to middle school, we can potentially recall the Bohr model of the atom with all those electrons locked into shells around a nucleus. And it's those little guys and their willingness to jump to more stable states when conditions allow that are really what this is all about. We could create those conditions through an electrochemical cell for electron movement, and by completing a circuit, they are more than happy to flow. Cells and batteries. So very simple. A cell, essentially, in our jargon, is just the individual unit that creates this energy, and it consists of an anode and a cathode, some electrolyte, and you get a positive and negative terminal. The battery is a connection or an array of these individual cells that we can use to bring the characteristics to the point that we really need them to be at. Series and parallel. So series, we stack them positive to negative, and we can elevate our voltages. We can multiply our voltages up through a series connection, so that two cells will give us twice the voltage of a single cell. And of course, in parallel, it's all about building a bigger fuel tank. We get more streams of electrons that we can use to get more energy, more capacity in our application. So the basic electrochemical cell, it's a redox, an oxidation reduction reaction. So we have the old Leo says Ger. So loss of electron is oxidation and gain of an electron is reduction. So in our most common application that most of us are talking about, it's often going to be a lithium thionyl chloride cell. And in that case, really our lithium anode is going to lose an electron, and ultimately that will end up over at the thionyl chloride side over in the cathode. So of course there is in the overall world of batteries, you have your primaries or rechargeable secondaries. And these chemistries have all come a long way over the years, and we've got lead acid, we've got hydride, and now these days the primaries, I shouldn't use the word primary, the key secondary technologies focuses around the lithium ion technologies. In primary, we all have alkaline batteries, and we've used them for many years. We have our lithium primary, which is our very high energy density batteries that, for the most part, we'll be talking about today. Things like carbon zinc and zinc air. Just a general feel for the energy densities. It really, we can see that as the technologies have come along through the lead acid years, the nickel metal hydride NiCads, we're really pushing this energy density to the right here, where 1 hours per liter, 1 hours per kilogram are really getting quite high. And they're primarily all focused in and around lithium technologies today. So why lithium? It's the lightest alkali metal. It provides the most power per weight or volume of any reactive metal. So yeah, lithium is really our superstar here. So when we talk about valence electrons, so maybe we don't all talk about that every day, but these are really just the fellows that are ready to party. They're the electrons in the outer shell of an atom that are ready to drive an electrochemical circuit. So both lithium and its nearest friend on the periodic table, sodium, for example, as we look at these top two, they're just bringing one electron to the party, one valence electron. But lithium brings his date in at less than 1/3 the mass. And so we essentially are getting a volume and weight benefit with lithium that is far exceeds anything else. So there's definitely several chemistries these days available. Lithium sulfur dioxide. We have highlighted here the lithium thionyl and lithium sulfurochloride, which we'll see are really the focus of a lot of oil patch and drilling work, and the really high temperatures. Lithium carbon monofluoride has certainly come on the scene and is showing some good results. Lithium iron disulfide, a fairly excellent cell for very low temperatures. Lithium manganese dioxide. These are all viable lithium technologies these days. So the lithium oxyhalides, the sulfurochloride, the thionyl chloride we were talking about, are really the two types primarily used in downhole applications. They have been adapted over the years for very high temperatures, high shocks, vibrations that we're all having to deal with and thrive through. Lithium thionyl chloride, perhaps the most common, is a 3.6 volt technology per cell, and sulfurochloride is a 3.9 volt technology. So just looking through the various lithium technologies that are out there, you can see that they all have a slightly different voltage that they work through, just based on the half cell reactions and how those stack up. But primarily the ones that we're using are at the highest voltage, which is the thionyl chloride and sulfurochloride cells. And this is where things really differentiate themselves, right? And this is why we've really focused in on these cells and why they have over the years become optimized for these extremely high temperature conditions. You get a lot of watt hours per liter and a lot of watt hours per kilogram. Your density is just far exceeds most of the other technologies that are available. So we can keep things stable. We will get into cell construction. Bob Fain will take us through the elements of cell construction that is critical.
Thanks, Craig. I appreciate the intro and what you said so far. Just want to remind everybody that there is a Q&A box. If you have any questions, please type away. We'll try to answer them at the end of this presentation. So anyway, I just want to talk about cell construction and how lithium, primarily lithium thionyl chloride or sulfurochloride, are constructed. So the next slide has a bit of a graphic on it. So first, you always have lithium anode, which is lithium metal. It's like a foil. Then you have carbon cathode, which is mostly consisting of carbon. Then you have a separator, which is like a non-woven paper. It's almost like toilet paper, that separates the two electrons. You have electrolyte, which in the case of the batteries that we use downhole is either thionyl chloride, mostly thionyl chloride, and sulfurochloride. It acts as a liquid depolarizer to help transport the lithium ions from the anode to the cathode. So without electrolyte, the battery is just not going to work. With electrolyte, the battery will discharge once the load is applied to it. And in the carbon, you have thionyl chloride that reduces the chloride ions, sulfur dioxide and sulfur. And lithium chloride also forms in the cathode and it's kind of redundant here, but sulfur and sulfur dioxide dissolved in the electrolyte. Just a couple of notes here. The rate capability of any type of cells depending on the common surface area between the lithium anode and the carbon cathode. So more surface area, more current that the cell can deliver. And there's also a separator paper between the electrodes, the anode and the cathode. This is very important that prevents the two electrodes from coming into direct contact to each other. If it does, then you would have a short circuit. So a separator paper is it's a vital part of the battery. So there are basically three ways to construct the cell, and we'll go through them here. But the Bobbin cell, it's a low rate cell. It's very simple in construction. It has one layer of lithium surrounded one layer of cathode. So, but it's only because of that low surface area, it's only capable of very low currents. I don't believe there's any oil field downhole high temperature application using Bobbin at this time. They're all using this next one or the one after that. And that is the moderate rate. It basically doubles the amount of surface area between the cathode and the lithium. You have two layers of lithium surrounding the cathode, like it shows in the pictures here. And by the way, the lithium is the silver gray material that you see in the upper right. And of course, you can see the white separator paper there as well. These are some examples of different cells available on the market. The 33, 127, 165 MRD double D is an electricum cell. It is one of the mainstream cells for MW applications. I still hear this today being referred to as a BEI cell. BEI stands for battery engineer, which became a part of electricum several years ago. But this cell is very rugged, safe, reliable. And you can also see these in C cells and double C cells. But the four manufacturers at the bottom all make very equivalent cells to moderate rates: Electrochem, Engineer Power, Vitrocell, and Tracer Technologies. The last type of construction is a spiral cell, and it's considered a high rate cell simply because the surface area between the lithium anode and the carbon cathode is very high, much more. It's wrapped up like a jelly roll or a spiral that you see in the picture on the left. So again, a lot of surface area between the electrodes gives it lots of current capability. This type of cell always requires the cell fuse installed on it. The other two types do not necessarily require cell fuses, but a spiral cell, if it was short circuited, it could result in an explosion. So it's made much safer by including a cell fuse. Some of the spiral cells are not suitable for high shock, but some are ruggedized, such as these showing here. Electrochem's Vitrocell and Engineer Power all make high rugged shock capable spiral cells for downhole use. This shows a chart of different rate capabilities, or relative rate capabilities. You can see the top line shows a double D moderate rate, whereas the double D high rate, the second line, you can see it's almost or more than double the current capability of a moderate rate. Same with the double C's, D's, C's. So the spiral will give you over twice as much current capability versus a moderate rate. So I'd like to hand it over to my colleague Mike. He wants to talk about some lithium battery performance challenges.